Right. Another aspect of the dot product is to find the angle between two vectors. So suppose we're asked to find the angle between 3, 9 and 4, -5. And we know that there's two ways to find the dot product. That you can find the dot product as u dotted with v is the magnitude of u times the magnitude of v times cosine of theta. And then also u dotted with v, you can find it doing ax plus by. Multiply the x components together and the y components together. So if I do the dot product using the component form, I'm looking at 3 times 4 plus 9 times -5. And so my dot product here is going to be 12 minus 45. It's going to be a negative 33. Yeah, negative 33 in there. But you can also calculate that as the magnitude of u times the magnitude of v. Oops, I'm missing a set of bars there, times the cosine of theta. And so what I can do is if I calculate those individually, the magnitude of u would be the square root of 3 squared plus 9 squared. It's going to be the square root of 9 plus 81. It's going to be the square root of 90. And the magnitude of v is the square root of 4 squared plus -5, quantity squared. So it's going to be the square root of 16 plus 25, which is 41, the square root of 41. And so I have that negative 33 is equal to the square root of 90 times the square root of 41 times the cosine of theta. Or if we want cosine of theta is equal to negative 33 divided by the square root of 90 times the square root of 41. And then I can use my inverse cosine to find out what the angle is. And the nice thing about that, maybe if I draw just sort of a quick picture, I'm traveling over 3 and up 9. Here's my vector, my first vector, u. And 4, -5 would be, so a little bit farther over, and then down 5, 4, -5 would be roughly there. What I'm going to end up here is an angle that's greater than 90 degrees. But the nice thing about cosine is it works just fine when the angle is greater than 90 degrees. So we should be able to come up with that value nicely. So if I'm working in degrees, let's just do the math there. Negative 33 divided by the square root of 90 times 41. I'm coming up with something like a negative 0.543. 543, that's kind of a fun number. Negative 0.5432. The next digit's a 5, so unfortunately it doesn't continue on with that nice pattern. But if I use the inverse cosine, it tells me that theta in degrees would be something like 122.9 degrees for the angle between those two. And that gives us the nice value up there if we need to find the angle. It's not so bad when you're working in 2 dimensions. We could probably figure that out by finding the individual angles and the angle in this part and the angle in that part and adding them together. But the real useful part is when you're dealing with 3 dimensions. In 3 dimensions, you've got spaces that are maybe you've got some vectors out in space. Let me stop my sharing here for just a minute. Stop share. So you can look here at my picture. Ooh, my vectors are getting mixed up there. But you've got a couple of vectors out there in space, and you don't really know what that orientation is on those. All right, let me stop my blurring background. You can see my messy office there. All right. So if you're looking at vectors out in space, you're looking at the angle in between those two, and you can have some sort of weird orientation, but you can nicely find the angle that's in between those two, regardless of what orientation you have. So on those two, if you got the vectors, it's kind of nice to find those with this dot product in there, especially in 3 dimensions. But we do the same kind of thing, that we know that if you've got the vectors u and v, if I call this the vector u and this the vector v, I know that I'm going to find u dotted with v 2 different ways. One way is I know it's the magnitude of u times the magnitude of v times cosine of theta. And the other way is to do it with the component forms. So it's going to be 1 times -10 plus 0 times 1 plus 2 times 5. So I'm going to have the square root of 1 squared plus 0 squared plus 2 squared multiplied by the square root of -10. Include that negative with your squaring, plus 1 squared plus 5 squared times the cosine of theta equals to -10 plus 0 plus 10. And so I'm going to have the square root of 5 times the square root of 126 times the cosine of theta equals, 0. And so I know that the cosine of theta equals 0 divided by the square root of 5 times the square root of 126, which is just 0. And so if the cosine is equal to 0, well, the cosine is equal to 0 at 90 degrees, or pi over 2. So theta is equal to pi over 2, or 90 degrees in there, between those two. 90 degrees in there. And so that's sort of an interesting feature. If you get u dotted with v to equal to 0, and assuming that the lengths aren't 0, that means that the cosine has to be 0 in there. If I'm getting 0 and these two lengths are some sort of number out here, the angle's got to be 90 degrees. So if u dotted with v is equal to 0, then u and v are what we call orthogonal. When we talk about fancy sort of things. So orthogonal is a fancy way to say perpendicular. We have the concept of perpendicular in 2 and 3 dimensions, but sometimes we get crazy with vectors and use 4 and 5 and 6 and 8 vectors. And so this concept of orthogonal comes in there. It took me a long time to kind of get that relationship, but orthogonal just means perpendicular in a 2 or 3 dimensional case, but just kind of a new fancy word for perpendicular. But we don't really have the concept of perpendicular in multiple dimensions beyond 3 or 4 dimensions or 5 dimensions. So we introduce this word orthogonal, but in 2 and 3 dimensions, it means perpendicular. So if our dot product turns out to be 0, assuming that we're dealing with, well, even if we are dealing with non-zero, if one of our vectors is the 0 vector, the 0 vector is technically perpendicular to every other vector, even though it has no length in there. We call it orthogonal in there. But if their dot product is 0, we know that the two are perpendicular or at right angles. And so we can do this dot product, use this product, this notion of dot product, to find the angle between vectors. So the two vectors that we're looking at out in space are actually at a 90-degree angle. However, those are oriented out there. They are perpendicular to each other. So that's kind of a useful tool, kind of an interesting fact. But we use the same process, that we have our two representations of the dot product as the magnitude of u times the magnitude of v times the cosine of theta. And then we have this component way of calculating. And we can use those two of them together to find the angle that's in between the two if we don't know the angle in between the two. Kind of a fun calculation to do.